browser.
Thank you. Hi, everyone. This is Sue. I'm going to tell you about map induction. This work is in collaboration with Aidan Curtis, Marta Creven, Josh Tannenbaum, and Ela Fee. And so we all know that humans are expert explorers and foragers. So when we go to new environments, say this convention center, we very efficiently explore and navigate these new environments. And so the question is, how do humans so efficiently explore new environments? And can we build artificial systems that can do the same? So to answer this question, we propose a map induction hypothesis, which suggests that as humans are exploring new environments, they are really predicting the unobserved, the maps of the, they might be representing the maps of unobserved spaces based on reusable regions from observed parts of the environment and from other familiar environments. So for instance, in a berry foraging task, one might be able to anticipate the landscape of hills will continue in the same pattern, and that the distribution of berries in unobserved spaces will be similar to that in the observed spaces. You can also more formally think about map induction as inferring the program underlying an environment that may have generated that environment given past observations. So to test the map induction hypothesis, we propose a map induction task which consists of 3D virtual environments that have a regularly repeating structure and rewards embedded into it. These are human behavioral experiments where we ask human subjects to explore and forage in these environments. And the task is to collect the maximum number of rewards possible, which are embedded as diamonds in these environments, in a constrained amount of time given to them. So we also formalize the map induction hypothesis by building map induction-based planning models that have 4 core components. So the first one is a region extractor that extracts region primitives from observed parts of the environment. The next is the map generator that composes these region primitives using an underlying probabilistic grammar and generates a set of map hypotheses. So this underlying grammar has transformations like reflections, rotations, scalings, and so on. And then the map inference module infers a probability distribution over the set of generated map hypotheses. And this distribution is then used by the planner to plan the next steps in the environment. So the planner that we use is a partially observed Monte Carlo planner that kind of approximately solves an underlying partially observed Markov decision process using a Monte Carlo tree search algorithm. So we consider 3 main model hypotheses. The first one is a baseline uniform model that doesn't use map induction. So it assumes a uniform distribution over the existence of wall, reward, or an empty space in the unobserved parts of the environment. So you can think of this as an unconstrained large distribution of possible maps. The second one is the maximum a posteriori model that uses the most likely map from the generated distribution of maps to plan. And the third one is a distributional model that uses the entire distribution of maps that the map generator has generated in order to plan the next steps in the environment. So here I show a contrast between the uniform model and map induction-based models. You can see the uniform model on the left does exhaustive exploration because it doesn't have any spatial priors, whereas the map induction-based models are predicting and inferring the map of the environment in an online way, updating their estimate of the map at every time step. And so they can predict where they are more likely to find the rewards, and hence this leads to more efficient exploration. So we find that map induction is critical for human-like optimal exploration. So here in panel A, I show the trajectories of a representative subject. And in panel B, I'm showing the averaged heat maps, visitation heat maps that are averaged over all the subjects. And you can see that after having visited a few units, the subjects are able to induce the rest of the map, and they go directly to the locations where they're more likely to find the rewards in all of these examples. Also, as expected, we find that the uniform model does exhaustive exploration, whereas the map induction-based models, both distributional and maximum a posteriori model, selectively explore the environments and hence are closer to humans in terms of how much, what fraction of environment they're observing. If we plot the log likelihoods of these models conditioned on human behavioral data, we find that map induction-based models explain human behavior better than the uniform model. Furthermore, we also find that humans build a distribution of possible maps through map induction. So in this subsequent experiment, we embedded color cues in these virtual environments, and the rewards were distributed based on these color cues. And we find that here, the map induction based model, that is the distributional model, actually predicts the human behavior better than even the maximum a posteriori model. So in conclusion, we found that humans build a distribution of possible maps through an inductive process after seeing a partial piece of an environment. And more importantly, this distribution is a constrained distribution as opposed to an unconstrained large distribution used by a uniform model. This map induction process is a conceptually new way to think about how humans navigate through a world in zero and few shot settings. We formalize this hypothesis computationally by combining a Bayesian map induction model and an approximate belief space planner. And we show that, and we find that map induction significantly improves the exploration performance of the state-of-the-art partially observed Monte Carlo planner. So that's all from me today, and if you are interested, please drop by my poster today and we can chat more.